Hello and welcome to another one of our online lecture videos for differential equations. And here we're going to talk about the method of elimination again. We're going to continue what we left off with last time. So we say the method of elimination continued, or method of elimination round. How does that sound? We're going to use the method of elimination to find the general solutions of the linear system. We've already presented this material in the previous video, so we're just going to jump on in. I'll explain along the way. We're going to see that there is something a bit different here, where now we're introducing these functions of t. I want you to keep in mind what we said last time, though, that x is a function of t and y is also a function of t, and that there's some relationship between x and y when we build their general solutions. But I want you to keep in mind that t is the input, t is the independent variable, and the differentiation that we're doing, finding x prime and y prime, and if we have higher order derivatives as well, that's all a differentiation with respect to t. Let's take a look at this first example. So we have x prime equals 4x plus y plus 2t, and we have y prime is equal to negative 2x plus y. Now, it's up to you how you want to sort of proceed with this, and it really doesn't make too much of a difference otherwise. What I might do is I might take a look at this first equation and say, all right, I can get y by itself and solve for that in terms of x's and x primes and some t's and stuff like that. And that seems like a good starting place. So here, if I solve for y, it means y is equal to, we have x prime, I'm going to subtract 4x over, I'm going to subtract 2t over. And so now I have y in terms of all of these other non-y things. And if I differentiate this, that means y prime is, here we get x double prime, we get minus 4x prime, and keep in mind, t is our variable. So here I can actually differentiate this last term for real. The derivative of negative 2t gives me negative 2. So now I have expressions for y and y prime, and I can go into this other equation and I can replace. So we'll go ahead and we'll say, okay, well, we do this in a bit of a different color so they don't run into each other. But y prime, all the way on the left-hand side, I can replace with x double prime minus 4x prime minus 2 equals negative 2x, I'm going to keep, plus y, and I can replace y with x prime minus 4x minus 2t. Now, since I have this function of t, what I'm going to get isn't going to be homogeneous, non-homogeneous, right? So I want to try to get all of my x's and x primes to the left, and then all of my function of t and this constant term that I have as well over to the right-hand side. So x double prime is going to stay where it is. Here I have minus 4x prime, but I got to subtract x prime over, so that's negative 5x prime. I'm going to move that minus 2, so I'm going to skip over it now. And what else do I have? I have negative 2x minus 4x. That's a negative 6x on the wrong side. I'm going to add it over. So we have plus 6x. And then equals, I'm going to add the 2 over, and we have 2, and then this minus 2t. So this gives me everything in terms of x and its derivatives, and then the function of t. No mention of y or y prime or y double prime anywhere. And this is a good starting point. Now what I'm going to have to do, treating this as something that's non-homogeneous, is I have to use that method of undetermined coefficients. And prior to doing that, I want to take a look at the homogeneous version of this differential equation. So I want to look at first x double prime minus 5x prime plus 6x equals 0. And we can solve this using the characteristic equation. So that's r squared minus 5r plus 6 equals 0, which I can factor this. So r and r to start, multiplying to 6 and adding to negative 5, we would say negative 2 and negative 3. So I get r is equal to 2 and r is equal to 3. And I can use this to build our complementary solution. So we can denote that x sub c, and that's going to be c sub 1 e to the 2t plus c sub 2 e to the 3t. And it's important that I do this first, that I can take a look at how my homogeneous solution looks, my complementary solution, so that when I go to make a guess for the particular solution, that I have that linear independence. Let me switch to a different color for that now. So looking at this right-hand side, 2 minus 2t, I want to model my guess for that particular solution using that method of undetermined coefficients. I want to model it after this, but making sure that I don't sort of step on the toes of any of the pieces of my homogeneous solution, my complementary solution. And it doesn't look like they're very similar at all. Here I have exponential terms, exponential functions. Here I just have a linear function on t. Since there's really no overlap or no threat there, I would say, let me try out a particular solution to the non-homogeneous, just modeled after this in a very generic way, a very abstract way, some constant a plus some coefficient times t. So just modeling by a linear function on t. It's basically as bare bones as it gets in a generic sense. And let me differentiate this twice over. So the first derivative, derivative a gives me 0, derivative of bt gives me b. And then the second order derivative just gives me 0. And let me substitute this in and see if this works, if I can solve for what a and b should be. So the second order derivative would be 0 minus 5 times the first derivative is b plus 6 times x. I'm replacing x with a plus bt. And that this is equal to 2 minus 2t. Okay, well, let's expand this out, see what happens. What's the worst that could happen, really, right? So I get rid of the 0. It's not doing anything, just taking up space and loitering, right? Negative 5b. Distributing through, we get plus 6a plus 6bt equals 2 minus 2t. And I want to set the like parts equal. So first of all, I have my t terms. I have 6bt on the left and negative 2t on the right. Setting those equal, I only want to focus on the coefficients. So focusing on the coefficients, we would say the 6b on the 6bt should be equal to negative 2t, or that negative 2 is really what I want to work with, the negative 2 on the negative 2t. And then anything that isn't underlined is my constant terms. So that means negative 5b plus 6a on the left should be equal to the 2 on the right. And this gives me a system of equations to work with, 2 equations, 2 unknowns, and I can solve this for a and b. In fact, solving for b happens pretty quickly. If I divide both sides by 6, b is negative 2 divided by 6, which I can reduce that to negative 1/3. So b is negative 1/3. So far, so good. And then I can plug that into the second equation and work with it. Let me jot down some ideas over here. Negative 5 times b is negative 5 times negative 1/3 plus 6a equals 2. So this is 5/3 positive plus 6a equals 2. Let me get a common denominator here. 2 is going to be 6 divided by 3. Same number, just brought to higher terms. Now if I subtract the 5/3 over, I get 6a is 6/3 minus 5/3. So then 6a is equal to 1/3. And if I divide both sides by 6, I get a is equal to 1 divided by 3 times 6, or that's 1/18. And so this actually worked out great. We were successful with this. So now I can go and I can actually write down what x is. We said that x is going to be a plus bt. But now I know what a and b are. So that means, and this for my particular solution, x sub p is a, which is 1/18, plus bt, which is a minus 1/3 times t. And now that I have my complementary solution and my particular solution, I can say that adding them together, the solution to the homogeneous and the solution to the non-homogeneous, is going to be my complete description for x at t, which is made up of these two pieces. So I got c sub 1 e to the 2t plus c sub 2 e to the 3t. And this particular solution to the non-homogeneous, plus 1 over 18 minus 1/3 t. And that's going to be my complete description for x at t. So I have the homogeneous, the complementary solution, and the particular solution to the non-homogeneous in there. So all of that gives me x at t. Now from here, it's a bit of a labor of love, so let's go ahead and see if we can find y. Because what is the relationship? It's right here. Y is equal to x prime minus 4x minus 2t. So I got to remember that and write that down for myself. X prime minus 4x minus 2t. X prime minus 4x minus 2t. And this is y. So you can see I got some more work to do, right? So I already have x here. If I find x prime, it's differentiating, I get 2c sub 1 e to the 2t, that's chain rule, plus 3c sub 2 e to the 3t. Derivative of the constant is 0. Derivative of minus 1/3 t is minus 1/3. So that's x prime. I'm also going to need negative 4 times x. And here, let me, instead of doing 4x and subtracting, it might be a little bit easier to keep track of everything if I just multiply in a negative 4x and then add. So here, negative 4x, if I multiply everything by a negative 4, that means I get negative 4 c sub 1 e to the 2t, negative 4 c sub 2 e to the 3t, negative 4 over 18, so I can reduce that, 2 on top and bottom, so that's a negative 4 is going to become negative 2, 18 becomes 9, and then negative times negative is positive, 4/3 t. And now to start, I still want to subtract 2t, and I can do that now, but I don't want to do too much all at once. I think it gets a bit confusing then. I go ahead and start by doing x prime plus negative 4x. So if I just sort of add these things up, I can see what I start to get. So here, 2c1 e to the 2t plus a negative 4c1 e to the 2t gives me negative 2c1 e to the 2t. 3c2 minus 4c2, these are like terms, gives me negative c2 e to the 3t. Think about sort of a common denominator here. 1/3 is really 3 over 9. I know, funny, right? I'm just drawing over what I drew over. But if I add these together, negative 3/9 and a negative 2/9 is going to give me a negative 5/9. And then I have this plus 4/3 t. Just comes along. But I don't want to subtract, I don't want to forget to subtract 2t. So to get y, I now have to subtract 2t from this. So take all this stuff from before, and then subtract 2t. But getting a common denominator is a good idea. So I would say instead of 2 times t that we're subtracting, think of that 2 like 6/3, because I can get a common denominator on the other t term. And here, just imagine I have all of those terms written in there. I really just want to rewrite everything and do that last bit of subtraction. So if you're following along, then we get y is negative 2 c sub 1 e to the 2t, negative c sub 2 e to the 3t, negative 5/9. And all I really had to do is subtract the 2t, which I have here. I can combine it with its like term. 4/3 t minus 6/3 t gives me negative 2/3 t. And definitely not a small feat. A lot of work went into this. But we now have our general our general solution for y at t, right? So we're all done with this now. So we had x at t here. And then with the relationship between the y and the x stuff, we got y at t here. Let me just y, you can see it's a function of t, but y at t is this stuff. So, you know, a little bit of work, but not too dissimilar from what we were doing before, just building on it, now talking about something non-homogeneous. Let's see another example. Here we have x prime is equal to 2x minus 3y plus 2 sine 2t. Y prime is equal to x minus 2y minus cosine 2t. It really doesn't matter where you get started with this. For example, you could, work with the first equation. Looks like you could solve that probably best for y since it has x and x prime in it. I actually prefer the second equation though. I think it might be nice to solve that for x in terms of y prime y and a function of t. But it really doesn't make a difference. So if you do this differently than I'm doing it now, you'll still arrive at the same result. Here, if I solve the second equation for x, we'll see x is equal to y prime. I'm going to add the 2y over and add the cosine at 2t over. So I have x in terms of all of the y stuff and some t stuff, right? Now, if I want to find x prime, because the other equation calls on that as well, I would just differentiate. So we say y prime becomes y double prime. Here 2y becomes 2y prime. Derivative of cosine of 2t, this is the function of my variable. I can actually differentiate this very organically. The derivative of cosine gives me negative sine of 2t, and chain rule gives me the inner derivative, which is an extra factor of 2. So I have x and x prime now to work with, and I want to plug those into this first equation. So say, well, how is that going to look? Well, here x prime, I'm going to replace that with y double prime plus 2y prime minus 2 sine at 2t equals 2 times x. So imagine I multiply x here through by a 2. So I won't show that work, but I'll go ahead and I'll write the result. So 2 times x, that gives me 2 times y prime. That gives me 4 times y, right? 2 times 2y. And then 2 times cosine 2t. And then minus 3y, I can leave it the way it is and rewrite it. And then 2 sine 2t, I can just write that. So now everything is in terms of y's, y primes, y double primes, and functions of t. No mention of x or its derivatives anywhere in here. And that's the idea, that's the goal, right? Now from here, I want to get all of my y stuff and its derivatives over to the left. I want my function of t, all of that stuff and any constants to be on the right-hand side. Okay, so let's go ahead and do that. So y double prime has no like terms. I can keep it where it is. The 2y prime, actually there's a 2y prime on the other side as well. So those are going to just cancel, right? I subtract it from both sides, it's gone. I'm going to move this negative 2 sine t over, so I'll skip over that. Going here to the right-hand side, I have 4y minus 3y, which is plus 1y, but I got to move it over, so that's going to be minus y. So I moved these, and then equals. I have this 2 cosine 2t that's there, and I'm going to add this 2 sine 2t over. It's going to join here with the 2 sine 2t that's already there. It's going to give me in total 4 sine 2t. So just moving this stuff around, having a good time, enjoying the elimination method. And I see this is a non-homogeneous differential equation, so I have to start with the homogeneous version of it. So I'm going to go here and say y double prime minus y equals 0. What are the solutions to this? And we can work with our characteristic equation, so that's r squared minus 1 equals 0, which I can factor this, right? So that's going to give me r plus 1, r minus 1 equals 0, which is going to give me two values for r. R equals negative 1, r equals positive 1. And from this, I can build my complementary solution on y. So y's complementary solution is going to be c sub 1 e to the minus t plus c sub 2 e to the t. So just working with our characteristic equation there to build our complementary solution. Now that I see what that looks like, I want to turn my attention back to the non-homogeneous differential equation and think about working with that method of undetermined coefficients. If I'm looking here at my complementary solution, I see that it's very different than what I have on the right-hand side of my non-homogeneous differential equation immediately. e to the minus t and e to the t, very different than cosine of 2t and sine of 2t. So that means I'm sort of in luck. For my particular solution to the non-homogeneous, I can just model my guess based on how this right-hand side looks in a very generic fashion. So we would say some constant a times cosine of 2t, I don't want to change the argument, the stuff inside, and then plus some constant b times sine of 2t. And I want to differentiate this twice over to find the second order derivative. So the first order derivative is going to give me negative 2a sine of 2t, and then I'm going to get 2b or not. That is the question. It's a little Shakespeare joke for you right there. A little Shakespeare joke, but it's 2b cosine 2t. And then if I differentiate again, second order derivative is where we're headed. I'm going to get minus 4a cosine 2t. And then here I'm going to get a minus 4b sine 2t. Looks good. I actually don't really need the first order derivative. I need the second order derivative, which is why I wanted to find it. But now I can go ahead and plug into this y double prime minus y. So y double prime minus y. I'm just writing myself a note here because I'm zoomed in, right? 2 cosine 2t. 4 sine 2t. Now if I go ahead and do the subtraction, let me switch colors. And let me just sort of like look at these things and do the subtraction. So y double prime minus y, negative 4a cosine 2t minus a cosine 2t gives me negative 5a cosine 2t. And negative 4b sine 2t minus b sine 2t, that's negative 5b sine 2t. And this should be equal to this right-hand side, which is 2 cosine 2t plus 4 sine 2t. So just setting those like coefficients equal, on cosine of 2t, negative 5a should be equal to 2. And on sine of 2t, negative 5b should be equal to 4. So these solve relatively quickly, right? A is going to be a negative 2/5. And b is going to be a negative 4/5. Not too bad. And now I can throw these in to build this particular solution. We did that in the pink. So that's a cosine 2t, and a is negative 2/5 cosine 2t, and then b is minus 4/5, and that was sine at 2t. All right, negative 4/5 sine at 2t. And now I can build my overall solution for y. And we're saying that if we take the complementary solution for y and add to it the particular solution to the non-homogeneous, then this gives us our solution for y at t in full description. That's c sub 1 e to the minus t plus c sub 2 e to the t. Make that look like an e kind of. Well, this one too, right? What's happened to my e's? And then plus the particular, so that's minus 2/5 cosine 2t minus 4/5 sine at 2t, and this is the general solution for y. Looks great to me. Okay, but we got to find x, right? And there's some relationship between them. Where is it? Right here. X is y prime plus 2y plus cosine 2t. So say it with me. Y prime plus 2y plus cosine 2t. Y prime plus 2y plus cosine 2t. And that is x. All right, let me double check. Because I'm so old, I can't remember. I say these things out loud to myself, and I'm just like, I'm a goldfish. I don't remember what I even just said. Y prime plus 2y plus cosine 2t. Bam. Any of those problems can be fixed with additional coffee beverages, but I have not had enough. So let's go ahead and find y prime. bring us on our way. If I differentiate here, I'm going to get chain rule, negative c sub 1 e to the minus t. Here, pretty standard, right? C sub 2 e to the t, maybe my favorite derivative of the day. Here, differentiating cosine gives us minus, so flips the sign, so plus, times an extra 2 from the inner derivative, so that's a 4/5 sine of 2t. Here, sine doesn't flip the sign, so minus 4 times 2 from the inner derivative gives me 8/5 cosine of 2t. And I want to add this to 2y, so if I do y and I double it, that's 2 c1 e to the minus t plus 2 c2 e to the t. And then here 2 times 2, so that's going to give me a minus 4/5 cosine 2t. And then times 2 gives me a negative 8/5 sine of 2t. And I am going to want to remember to add a cosine of 2t, so don't let me forget that. In fact, I'll even just like circle it. Don't forget me. Okay, so first I want to add y prime and 2y together. I should be able to handle that, right? So y prime plus 2y, that's going to give me, so these are like terms. 2c sub 1 minus c sub 1 is c sub 1 e to the minus t. 2c sub 2 plus c sub 2 is 3 c sub 2 e to the t. And so sort of have to look diagonally here. Negative 4/5 cosine 2t minus 8/5 cosine 2t gives me a negative 12/5 cosine 2t. That exactly lined up perfectly. And then same idea here. Negative 8/5 plus 4/5 gives me negative 4/5 sine 2t. And then all that's left is I want to make sure that I add a cosine of 2t. So I want y prime plus 2y plus cosine of 2t is what I want to remember to add, cosine of 2t. So it's going to be all of these terms that I have plus cosine of 2t. But here, if there's a like term with it, right? So cosine of 2t, let me think about it with the coefficient. The coefficient is 1, but I can make that a 5/5 cosine 2t and just combine it with the other cosine 2t term that I have. And that is going to be y prime, I got it, 2y, I got it. I'm going to add the cosine 2t, I'm ready for that. So that's going to give me my general solution for x. So x at t, that's going to be equal to c sub 1 e to the minus t, rewriting it, plus 3c sub 2 e to the t. Here I'm combining these like terms. Negative 12/5 plus 5/5 gives me negative 7/5 cosine 2t. And then minus 4/5 sine at 2t. Yes. And was it easy? No. Was it fun? Yeah. I have my general solution for x at t. And we have general solution for y at t from previous. So it just sort of brings our elimination method up a notch. Dealing with non-homogeneous equations, of course, always introduces new ideas. Let's take a look at one last example here. Method of elimination. We're going to see this is a little bit different for a couple of reasons, but I'll mention those along the way. I won't spoil it now. So here we can go ahead and think about how we want to start. You know, it doesn't really matter. So I might even look at the second equation and say I like working with a 2 and an 8 more than a 5 and a 2, a negative 5 and a 2. So I might go to the second equation, but that's completely arbitrary. It's just a decision that I've made. You got to make a decision at some point, right? Let me solve it for x, because I have y double prime and y otherwise. So I want to try to isolate x then. So if I add 8y over, y double prime plus 8y equals 2 times x. Solving for x, I just want to multiply both sides by 1/2. So I'll say x is 1/2 y double prime plus 4y. So just dividing by 2. And I did switch sides. I wrote x on the left. Again, just a preference of mine. Now I can find x prime, but I have to go all the way to x double prime. So x prime is 1/2 y third order derivative plus 4 times y prime. And the second order derivative, x double prime, is 1/2, we have y's fourth order derivative plus 4y double prime. And this is another piece that I'm going to have to be working with. Now I have this equation. I'm just going to rewrite it here. X double prime equals negative 5x plus 2y that I can now substitute into. I'll do this in a different color. So x double prime on that left-hand side is 1/2 y's fourth order derivative plus 4y double prime equals, and then negative 5 times x, just think about multiplying by a negative 5 here, gives me negative 5 over 2 y double prime, and then negative 5 times 4 gives me negative 20y, and then plus 2y. Something worth mentioning at this point, or maybe you noticed it already, is that what I have here is in fact a homogeneous differential equation. It's going to be, right? So there's no function of t laying about, and that's going to make things a little bit nicer. But you're also noticing a second distinction here is that we have much higher order. So that's going to kind of make it, easier, but then more difficult. So it probably balances out quite a bit. Well, let's see what we get. So let's go ahead and move everything over to one side. And I'm going to move everything over to the left here. So I have 1/2 y's fourth order derivative. Let me get a common denominator. So I'm going to write 4 as 8 over 2 y double prime. I'm going to add 5 over 2 y double prime. I'm going to add the 20y over. I got to subtract with 2y over, and now it's equal to 0. So I just got to collect my like terms, right? So 1/2 y's fourth order derivative plus 8/2 and 5/2 gives me 13/2 y double prime. 20y minus 2y gives me 18y equals 0. And from here, since I don't really like having this leading coefficient, of 1/2 in particular, what I could do is I can multiply everything through by a 2. I have to do this to both sides of the differential equation. What we're going to notice is that here on the left, it clears that coefficient, so we have y's fourth order derivative. Here it gets rid of the fraction, so we have 13y double prime. 2 times 18 gives me 36y, and luckily 2 times 0 is still 0. So it's kind of not too much added expense to do this and a lot of benefit, right? Now from here, I want to work with my characteristic equation. So y's fourth order derivative, I replace that with r to the power of 4, plus 13 y double prime is r squared. 36y just becomes 36 equals 0. And I want to factor this. You'll notice that we skip over r cubed and r to the first in this polynomial on r. So factoring it, I can really get away with the usual method of factoring. But to start here in each parentheses, I want r squared, right? R squared times r squared gives me r to the fourth. And then it's that usual guess and check method where I'm saying, okay, what two numbers multiply to 36 and add to 13? I am thinking about 9 and 4, right? 9 times 4 gives me 36, and then a 9r squared plus 4r squared gives me that 13r squared. So factoring this wasn't too terrible, right? Definitely doable. And then I can work from here and say this means that r squared is equal to negative 9, or r squared is equal to negative 4. So then r is plus or minus the square root of negative 9. R is plus or minus the square root of negative 4. So we get these pure imaginary ideas here. R is plus or minus 3i. R is plus or minus 2i. And from all of this, we can build our solution for y. We were working with y. So let me just switch colors. What do we like? We like red. So y, our function of t, this is going to be c sub 1 cosine 3t plus c sub 2 sine of 3t plus c sub 3 cosine of 2t plus c sub 4 sine of 2t. And this is it because it wasn't a non-homogeneous differential equation. It was equal to 0. It was homogeneous. So this is just all of the pieces to our solution then for y at t. So we have these pure imaginary. So we got c1 cosine 3t, c2 sine 3t, plus c sub 3 cosine 2t, plus c sub 4 sine at 2t. Now all that's really left is to find x. I got a feeling that's not going to be the easiest thing to do, but I also got a feeling that we are capable. We can do it. Probably not too difficult, probably just a lot of stuff, right? And let me see. I'm nervous, which is why I'm stalling. What is it? Oh, it's not so bad. X is 1/2 y double prime plus 4y. So 1/2 y double prime plus 4y. Say it with me. 1/2 y double prime plus 4y equals x. Yes. Nailed it. Perfect. So let's differentiate. I have y. I want to find y prime. So derivative of cosine gives me negative sines. Think about chain rule, so that's negative 3 c sub 1 sine 3t. Derivative sine gives me cosine, so that's 3 c sub 2 cosine 3t. Here I'm going to get a negative 2 c sub 3 sine 2t. And then here I'm going to get a plus 2 c sub 4 cosine 2t. But I want y double prime. So differentiate again. So this is going to give me now negative 9 c sub 1 cosine 3t. This is going to give me negative 9 c sub 2 sine of 3t. This is going to give me negative 4 c sub 3 cosine 2t. And then we're going to get negative 4 c sub 4 sine at 2t. And I want 1/2 y double prime. So let me do this, actually. You know me. You know how lazy I am. 1/2 y double prime. I'm going to get it. Just divide by 2. I can reduce here, but I'm not going to. First of all, because I'm lazy. Second of all, because I probably need a common denominator, so I don't know. We'll have to see. I think actually I could reduce there. So you know what? You should never strive to be lazy. You should always want to be a better person. I'm like mumbling it because I don't want to be saying it. You don't have to be a better person. Just be who you are. That's all I care. So he said negative 2 divided by 2 is really just, it was negative 4 over 2, so that's negative 2 c sub 3 minus 2 c sub 4 sine 2t. Okay. So I changed my mind. What else is new? And I want 4 times y. So let me go ahead and do that. I don't think I need a new color for that. 4 times y, I just want to multiply all this stuff by 4. Sure. Why not? 4 times y. What do we start with? Cosine 3t, so 4 c sub 1 cosine 3t plus 4 c sub 2 sine 3t plus 4 c sub 3, that's cosine 2t now, plus 4 c sub 4, and that's sine 2t. Right, just multiplying here, y, everything by 4. So 4 goes in front for all of these. And then I want to add these together, right? 1/2 y double prime plus 4y. So just to make this ready for adding together, I do want common denominators on the sine and cosine of 3t stuff. So 4, that's really 8 over 2. Don't make fun of my 8s. They're trying the best that they can. They're doing the best they can. Leave them alone. That's an 8. That's an 8. They look beautiful. And I want to add the 1/2 y double prime plus 4y together, of course. 1/2 y double prime plus 4y is equal to negative 9/2 c sub 1 cosine 3t plus 8/2 c sub 1 cosine 3t is a negative 1/2 c sub 1 cosine 3t. Again, like terms, gives me a negative 1/2 sine of 3t. These nice integers, right? Negative 2c sub 3 plus 4c sub 3 gives me plus 2c sub 3 cosine 2t. And same here, negative 2c sub 4 plus 4c sub 4 gives me positive 2c sub 4 sine of 2t. And this is 1/2 y double prime plus 4y, which is x. So this builds my general solution for x at t. Right there in the answer box. So it looks good. So we had y's solution from that using the relationship between x and then y and its derivatives, of course. We worked through to find x. So we got x at t as well. That is it for the section. Let me go ahead and put the homework in the homework jar. Take a look at that homework for the elimination method. If you have any questions at all about it, send me a message over on Piazza. Let me know on our online discussion board. I want to hear from you. I said at the very beginning, I think you're going to like elimination method. We're kind of done with the topic now as far as lecture is concerned. I want to know, did you like elimination method? Do you not like it? What do you like about it? What do you not like about it? Let me know. Let me know what you're thinking. Tell me what you're feeling. I want to hear from you, definitely. But otherwise, thank you so much for your time. I just want to remind you that no matter what, keep learning, keep dreaming, and always, always follow your heart.